Hello, this is the third lecture on neural networks for the Computational Intelligence course at TU Delft. If you recall from last week, we discussed the backpropagation algorithm. That was essentially exploiting the fact that there was a lot of redundancy in the gradient calculations, and therefore we could simplify the process of computing gradients a lot and speed up the learning process. So essentially what we saw is that the gradient at a particular layer could be computed by reusing gradients that we have already computed at previous layers. Then we talked about convolutional neural networks and how these were very good at processing image data. We discussed the convolution operator, which allows the network to be equivariant to translation. And this was good because that would allow us to, say, detect objects no matter where they're placed in the image. That was actually pretty useful. And the reason for this equivariance is that the weights are applied all along the image. So all pixels, all regions are essentially being weighted by the same weights, the same parameters. So this is known as parameter sharing. Then we talked about recurrent neural networks and how these were very good at processing sequence data. We saw two examples from natural language processing. And then we finally discussed the backpropagation through time algorithm, which was the version that we use to train recurrent neural networks. And the reason we have a different algorithm for recurrent neural networks is because the gradients, if you remember, depend not just on the weights at this at the current time step, but also at previous time steps. So the gradients basically just backpropagate through the entire sequence of samples. Today we're going to try to make a bit more sense of all these backpropagation algorithms because now we have the analytical expressions for computing those gradients, but because we don't have an expression for the loss, we can only estimate these gradients using data. And today we're going to see how this is done. First, we're going to talk about neural network design. So we are going to discuss how to choose the activation functions, how to choose the number of neurons, how to choose the number of layers in our network. We're also going to talk about model capacity, and that is basically the complexity of the neural network. Essentially, is the ability of the network to feed a wide variety of functions. And then we finally will go through the process of training a neural network and what things you need to keep in mind when you go through that process. Okay, so the material for this lecture is going to be the book by Ian Goodfellow. So here I have annotated the particular sections that you need to read. So this is chapter 5, chapter 6, and chapter 7. And this is what we're going to cover. And again, I don't want you to think that this is mandatory. So essentially, just read this if you're interested, if you like the topic, if you have some extra time. I think it's going to be useful. But in practice, you don't really need to read this in order to pass the exam, right? Like you should be good with just this video lecture and the slides. And finally, I have also here a link to a TensorFlow tutorial where I was actually going to do this in class. I was going to walk you through the tutorial, but unfortunately, due to the circumstances, I just have the link here so that you can basically try to understand yourself how this process of training, in this case, a convolutional neural network works. And the good thing is that this TensorFlow tutorial is very well explained. There are a lot of comments, so it should be easy for you to understand. But you can also email me questions if you have them. This is just to reinforce a little bit your knowledge on neural networks and to try to show you how they are used in practice. Okay, so first let's just start with how we choose the activation function. So the activation function is the choice that we make. It depends on whether we are talking about output neurons or we're talking about hidden neurons. So now we're going to discuss how we choose the activation function for our output neurons. And that depends on the actual task. So we could have a classification problem or we could have a regression problem. And depending on the kind of problem, we actually need one activation function or another. So the first activation function that we're going to talk about is the sigmoid function that you all already know about. So for k classes, if k equals 2, then we can use the sigmoid function. And if you remember from previous lectures, the sigmoid function has this form. So 1 over 1 plus e to the minus c. And I'm just going to try to reverse engineer and show you why this function has this particular shape, why this is the exact expression that we need. Okay, so in practice, we have that what we want to model is the probability of our level given our data and the weights. This is what we're trying to model with the neural network. So essentially the probability of y being equal to 0 given x and w, that will be the probability for the other class. And if we have two classes, if we call this p, this is 1 minus p, because the probabilities, as you know, need to add up to 1. Now, because the range of values that this probability takes goes from 0 to 1, it cannot take any value, just values between 0 and 1. And our output C at the last layer, so I'm just going to denote L is my last layer, that is essentially W, the weights at the last layer, times the activations at the previous layer, the output of the previous layer, plus B. This is essentially the formula that we had in the previous lecture. And now you see that basically these C's can take any value between minus infinity to infinity. All right, so it would actually be difficult to bound these C's so that they are within this range from 0 to 1. Instead, what we do is we try to transform this probability into another measure that is equivalent, but that ranges from minus infinity to infinity. So the first transformation that we apply is basically we take the ratio of the probability of one class divided by the probability of the other. So this ratio is called the odds ratio. And this is good because now we have that this value goes now from 0 to infinity. This ratio goes from 0 to infinity. But we're not quite there yet because we want our range to go from minus infinity to infinity. So what we could do is we could take the log of this odds ratio. So we have the log of p over 1 minus p. And this is essentially now, if we plot this, this essentially looks like this. So this will be 0.5. Here I have O, and here I have 1. So if I draw how this function looks like, it looks something like this. Right, so you see that this is basically, if you remember the shape of the sigmoid function, it looks like this. So this is essentially like a rotated version of the sigmoid function. Now, if what we're trying to model is this value here that goes from minus infinity to infinity, we're trying to model or fit this value using C. We can essentially write C equal to log of p minus 1p. And now, because I want to find this probability in the end, what I need is a value between 0 and 1. Let me just rearrange this and see how we can express this in terms of C. So how we can find the probability in terms of C. So essentially, this is equal to the e to the power of C is equal to p over 1 minus p. And then we can write this as p is equal to e to the power of C minus p e z. And then this is essentially p is equal to e to the power of C over 1 plus e to the power of C. And this starts to look a little bit more like a sigmoid function. So basically, if we divide both numerator and denominator by e to the power of C, then you will see that this term in the numerator is 1, then 1 over e to the power of C, that's e to the power of minus C, and e to the power of C divided by e to the power of C, that's 1. So we have 1 plus e to the power of minus C, which is essentially the sigmoid. So you see that basically what we did is we wanted to have our probabilities in the range, in a range that goes from minus infinity to infinity, so that we could model them using C. And then basically, to get back our probabilities, we needed to apply the sigmoid function. So that's the reason why the sigmoid function looks like this. Now, if we have more than 2 classes, so k is larger than 2, then the output y hat k, because now we have, say for instance, if there were 3 classes, we have 3 outputs. Is essentially equal to the probability of y being equal to k given x. And this can be modeled by the softmax function. So probably you recall from last week that I already introduced this function. And this is essentially the multivariate version of the sigmoid function. So what we do, if this is C1, C2, C3, what we do is essentially we take the exponential of each of these elements and we then normalize by their sum. So we get something that looks like a probability distribution. So for instance, we could get a value of 0.1 for the first output, 0.2 for the second output, and 0.7 for the third output. So this normalization factor just makes sure that the probabilities add up to 1. And you can show that essentially if you have 2 classes, you can this thing can be translated into the sigmoid function. All right, so that's for the multivariate classification problem. These are the activation function. This is the activation function that we use. What about for regression? So in regression, essentially we have that we want to model a function that could look like this, given some data points. And normally this function can take any value, right, from minus infinity to infinity. So now our output is not constrained like before. And therefore, what this means is that if C is the output of the last layer, and this is given by the weighted linear combination of the outputs of the previous layer, what this means is basically that now I can just take this as my actual output. So I can just have the identity here. because now this guy here takes any value between minus infinity and infinity. So this essentially matches what I need, right? So I don't need to apply any transformation. This is actually pretty useful, right? Because I don't need to think about any activation function anymore. Now for my hidden neurons, I can be a bit more creative here, because now I'm not constrained to any sort of values or ranges. So then I can just decide the function based on other characteristics, on other requirements. Okay, so again, one possible activation function will be the sigmoid function. And the sigmoid function, again, looks like this. So the sigmoid of z is essentially 1 over 1 plus e to the minus c. And again, if you recall, the sigmoid function was essentially had this shape here, something like this. It's a bit different, but you know. And then, sorry about that. And then what we see is that basically the sigmoid function takes a value, or the gradient of the sigmoid function takes a value that is different from 0 at all points. And that was good, right? Because that would allow us to apply the gradient descent algorithm as opposed to when we use the step function as our activation function. Now, this is useful, but at the same time, if we look at the gradients in this region and this region here, they're pretty much like very close to 0, because the lines here, or the slope here, is pretty much horizontal. So there's one issue with this activation problem, and it's called the vanishing gradients problem. Now, because of this vanishing gradient problem, we can actually see that because when our neuron saturates and we are in this or this region, our gradients will be very small, and therefore the gradient descent algorithm is not going to work as usual, because now we are not really moving away from the current set of weights, right? Like we cannot modify our weights by much, because the gradients are too small. So the steps that we're taking are too small for the algorithm to ever converge. All right, so instead what we could do is we could try to do something different, and perhaps try to add a certain slope there that would allow us to have larger gradients. So we're going to see how that is done in a different activation function. But then another problem that we face is essentially that now this function is not symmetric. So it's not symmetric. And what this means is that we have a function that is not symmetric with respect to 0. And essentially what that means is that the output, which is normally denoted by a, is always going to be positive, because this function is non-symmetric. You can see that our outputs are between 0 and 1, and therefore they're always positive. They're always larger than 0. And why is this not ideal? Well, there is an issue known as zigzagging that is provoked by the function, or the activation function, not being symmetric, zigzagging. And essentially what that means is that if I have the function itself, if I have my function, I cannot actually move in a different direction for every of the different weights. And let me show you what I mean. So if I have c being equal to w times the input or the output of the previous layer, this is my one particular layer, plus b of L, and I take the gradient of this, so the gradient of the loss with respect to WL. This is essentially could be written as the gradient of the loss with respect to Z, gradient of the loss with respect to ZL. I'm just skipping a few steps. From the backpropagation algorithm, you recall that I went through the entire sequence of operations, but now I'm just skipping those because this thing is going to be a constant, times the gradient of CL with respect to W. Now these W's are all my weights for this particular layer, and these A's are the input to that particular layer. And this thing is going to be constant for all my weights, right? We called this thing before, we call it the error gradient, and we denote it by sigma. So this is going to be constant for all these weights, for all these gradients. And this can take the value of plus or minus, right? It can be a scalar that can take any value, but it's going to be constant. It can be positive or negative. And then this guy here is A. So the gradient of this is A, the vector A. And we know that each element in this vector is greater than 0. What that means is then that essentially depending on what this value is, which is the same again for all my weights, for all the gradients of my weights, depending on whether this is positive or negative, we will be moving our gradients in the same direction, in that direction. So we will be moving all our gradients either on this direction, so on the positive direction, or on this direction. But we cannot move the gradients in this direction. This is not allowed, because this will mean that if this was W1 and W2, then W1 will be moving in the negative direction and W2 will be moving in the positive direction. But that's not possible according to this, because this is constant for both of them, is the same, and this is always positive. So they have to move either all in synchrony to larger values, or all have to get smaller and move to lower values. So what you see is that basically if I plot the loss function like a contour, so the loss function could look like this. This could be my minimum. The loss function could be something like this. And I start somewhere here. These are my initial weights. I'm just going to denote them by W0. And this is where I wanna end up. W star for optimum. Then what you will see is essentially that the path towards the minimum will be a zigzag. So we'll be zigzagging and moving towards the minimum. And this might take forever. So this is why an activation function that is not symmetric is actually not very useful. All right, let me just then explain how we can get this function to be symmetric. And for that, we use the hyperbolic tangent, tan h. And this is written as 2 over 1 plus e to the power of minus 2 times z minus 1. And the hyperbolic tangent has this shape. So the hyperbolic tangent is something like this. So there are two nice properties. First, this function is symmetric. So no zigzagging anymore, because now our values a can be either zero, larger than 0, or negative. And then another nice property is that if you look at the slope here, it's much more steep than with the sigmoid. which means that our algorithm might converge faster. But then we still have the issue with the vanishing gradients. The gradients at these locations are still very close to zero. Although we solved the symmetry issue, and we can converge faster when the gradients, when the values are around this region. We still have the problem of vanishing gradients. So there's a third common activation function. So that was our first choice. This is the second choice, and this might be the third choice, which is called the ReLU. And this stands for rectified linear unit. And this can be written as the max of 0, z. And as you probably guessed, this looks something like this. So 0 for negative values and z for positive values. So this solves our vanishing gradient problem. This is solved. But now what you see is that essentially this guy here, the gradients here, when we are in this position, are essentially zero, which means that if for a particular sample it turns out that the neuron is not firing, neuron outputs a value of 0, then it will also, the weights for that neuron won't be updated. So the same that happened with the step function, the fact that they were the gradients were always 0, that meant that we were not going to update our gradients using gradient descent. In this particular case, we're not going to be able to update the gradients of the neurons that are not active for a particular sample. And this is known as the dying ReLU. Because you can think of that if the neuron itself, the weights lead all samples towards this region here, then this neuron is not going to fire at all, and it might die and never recover. So this is the dying ReLU problem. The way it's solved in practice is sometimes by adding like a not very pronounced slope here. And this is known as the leaky ReLU. But we are not going to cover this one here. But just so you know, you can just solve this issue by adding a small slope in the negative for the negative values. And that's known as the leaky ReLU. And then another problem that we have is that the function is not symmetric again, so there's zigzagging. And finally, one extra problem is that the gradient at this location, the gradient at 0, is not defined. In practice, this doesn't really matter because when we compute the gradients with a computer, we're never going to get a gradient that is exactly 0. We're never going to get a weighted summation that is exactly 0. There will always be some machine precision, and therefore our gradient in practice will be always defined. So this is something that we shouldn't worry about when we apply these things in a computer. Okay, so even though there are still some issues with this function, this is by far the most common one to use nowadays, and it has shown that it's much more efficient than either the sigmoid or the hyperbolic tangent. Good. Okay, so let's just move on now. Now we're gonna talk about layers and neurons. and how do we decide how many layers and how many neurons we need in our neural network? So essentially what we see is that our first choice could be having just a single neuron. And you remember from the first lecture, having just one neuron meant that our decision boundary was linear. And what that meant is that if the two classes that we were trying to separate were non-linearly separable, then essentially this thing wouldn't find a solution when applying the update rule that we discussed in the first lecture. And therefore, this algorithm wouldn't be helpful when the two classes are not linearly separable. One good thing about this is essentially that the problem becomes convex and it's easy to optimize. A function that is convex. But in general, this one single neuron is not very practical because, we can only get linear decision boundaries. Okay, so there's a theorem called the universal approximation theorem that states that a multi-layer perceptron with a linear output layer and one hidden layer, or at least one hidden layer, and any squashing activation function. A squashing activation function is like the sigmoid function, which takes a range of values that goes from -infinity to infinity and maps them, squashes them to a range that goes from 0 to 1. So that's a squashing activation function. So if we have one output layer and at least one hidden layer, we can approximate any function provided that we give the neural network, we give the hidden layer enough hidden units. So this is a requirement. We need to have enough hidden units to be able to fit any function. All right, there's a few drawbacks. First, this doesn't guarantee that our training algorithm will find the global optima. And you can see that when our optimization task or loss in this case is not convex, like in this particular case, when this is not convex, it could have a shape that looks like this. And the training algorithm could essentially, if it started here, could essentially try to find the solution and get stuck here in a local optima. And if this happens, then the universal approximation theorem is no longer true, and therefore my model wouldn't be able to approximate any function. Another thing this theorem doesn't guarantee is that the model can generalize to unseen data, and we'll discuss this in a minute, but this is related to overfitting. And this is basically just that our model sort of memorizes our data, but then it doesn't generalize to unseen examples. And finally, this was the one of the main requirements, but enough hidden units doesn't put any bounds on the number of units, and in practice this number could be infinitely large. So we might need an infinitely large amount of neurons in order to be able to approximate any function. And what you see is that normally deep learning engineers prefer to add more layers. So it's better to add more layers than to keep adding neurons to the same layer. So it's better to add more layers than to add more neurons in practice. And the reason for this, it's just empirical, but you can think that by adding more layers, sort of the complexity of the function and the flexibility of the function improves faster than by just adding more neurons. Okay, so let's talk about model capacity. So the model capacity basically tells us how good our model is at fitting a variety of functions. And this is important because we want a model to generalize to unseen data. So we want to find the right capacity that allows our model to fit unseen data. Okay, so we want our model to perform well when given unseen samples. But in practice, we're training our model using the training error. So in practice, what we see is that from previous lectures, we know that the loss is essentially y, is essentially the true label. So y of our training set minus the prediction that we make, and we take the second norm of this. So again, if you recall, this is just the notation for the squared error. So y train, this is essentially the same, y hat squared. This is just notation. Okay, so normally what we have is we have a training set, and we have some inputs, and we predict the outputs, and we try to minimize the error of our training set. Now, because we want a model to generalize well, that's the end goal. We want a model to not just be good with the samples that are in the training set, but be good with any other samples, because in the end we want to make predictions in general, not just with our training samples. We already know the labels of our training samples. We want to make predictions on new samples that we have never seen. So our goal is to generalize well, and therefore what is normally done in practice is that you take your data set and first you take a subset of samples for training and you leave out another subset for testing. So these samples are not used for training. These samples are only used for testing, and they are basically useful because they allow us to evaluate the performance of our model and perhaps compare it to another model. So we could have a test set that we could use in two different models, maybe two different neural networks but with different architectures, and we then use a test set to compare the performance of these models. So essentially what we're trying to optimize is not this function, but this function, y test. And we do that implicitly by optimizing this function, y hat. And again, this is y test minus y hat squared. All right, so you see that basically if we plot these two functions, so if we plot this on the plane, essentially what you will see is that normally, so this could be my training error, this could be the number of updates, the number of times I updated my parameters. This could be my loss. Let me just make this a bit more vertical because it looks pretty bad now. So we could have something like this, and then my test error will be always larger than the training error because it's a data set that I have never seen. And what happens in practice is that if we train too much, if we update our values too much, then our test error starts increasing again. And this is related to the problem of overfitting. We're going to discuss that in a second, but in general, it's also important that the samples, both in the training and the test set, come from the same distribution, and What that means is that they need to be identically distributed. They need to be independent. That's a requirement. They need to be independent from each other. There shouldn't be any correlation between samples, but they also need to be identically distributed. Not only within the same set, so not only within the training set, but also across the two different sets. So what that means is essentially that if I have a distribution for my training set, I cannot have a different distribution for my test set. The distribution for my test set needs to be the same. So the data generating process needs to be essentially the same. Okay, so that's a requirement for using this, for evaluating my model on a test set. It needs to come from the same distribution. Okay, so model capacity, as I mentioned before, is the ability of the model to fit a wide variety of functions. So we want our capacity, our model, to be able to fit the kind of functions that we're trying to model. And what we see in practice is that, for instance, we could have a data cloud, a set of data points that looks like this, maybe. So if the model capacity is very restricted, if the model capacity is not high, we could have a model like this one, and this is just the linear regression now, but it applies for neural networks as well, which will look like this: Wx plus b. This is x and this is y. So what we'll have here is that if we plot this, this will look like a straight line. Now, this model cannot feed this data here, so it does not have the capacity to feed this data. It doesn't have the ability to model the behavior of the data, and we call this problem underfitting. On the other hand, if our model has a very high capacity, and we still have the same data cloud, so we could have a model that will look like in linear regression again, have a model like this: Wx plus W is 1, 2, Wx squared plus W3 times x cubed, and so on. We could have a very complex model, and what we'll see then is that if we train that model, we'll get a curve that will look maybe something like this. So it will basically memorize all the samples, but it won't generalize to unseen data. So then if we receive a new sample, say somewhere here, then our predictions can be actually pretty wrong, right? Because our model has so much flexibility that it has just accommodated to our data. And this is not where we actually want. We want a model to generalize to unseen data. So in practice, we need a model that has exactly the same, the necessary capacity. Okay, so essentially what we want is, in this particular case, what we need is a model, and because we know this is a parabola, we need a model that looks like this. So we just need second order terms, and then we'll have a model that looks like this. And this will be the right capacity for this data cloud. As you know, in neural networks, we cannot really decide to create these features in particular. And actually, this will feel more like engineering, right? Because you then first will have to look at the data and then figure out what kind of features we need. In the neural network approach is much more flexible, and therefore we cannot decide beforehand what features we need. So it's very common to find ourselves in this kind of problem when we have a model that is too complex and it overfits the data. Because I mean, to solve this issue, basically with a neural network, you just need to add more layers or more neurons. But to solve this issue, you don't really really have a choice, right? If you cut too much, then you might move towards you might shift your problem to underfitting. So finding the right amount of complexity is not that easy. And you also see that if we plot the error, the loss against capacity, what you see is essentially that my training loss will decrease together with my capacity, because like you become very good at fitting the data, you become very good at remembering the data, the training data. But my test error, because I never seen that data, will eventually start increasing as I make my model more and more complex. So this gap will eventually increase. And again, we saw that here one way of preventing overfitting would be to stop before my test error increases too much, right? So before I allow the model to remember the data itself, I stop, and then I get a very low error. So I might get a curve that looks like this one, even though my model is complex, because I don't allow it to converge to the optimal for the training set. I don't allow it to overfit.